Assalamu alaikum everyone. So till now we had completed the two simulations in the Ansys. One is actually a hole in a flat plate and another one is a signpost. So those were basically the structural, static structural analysis. So you performed the analysis and you had determined the deformation, stress, strain and so on. But here on the activity 3, we're going to introduce you to, the CFD analysis, the computational fluid dynamics, where we'll be actually analyzing the flow and the fluid flow through a pipe and so on. So here till now we had used the static structural analysis in the Ansys workbench. But now for this experiment, this activity 3, we'll be actually going into some very introduction with the Ansys Fluent. So we're gonna actually do the two simulations today. One is basically here, the first one. This is a 2D simulation, and the second one is this one. We're going to perform this two simulation on the Ansys Fluent today. So before starting to the Ansys Fluent, we're going to start or discuss some very basics and very differences with the static structural analysis. As you know, in the Ansys static structural, you had actually performed analysis on the overall shape of the body, the body of the object. So if I want to know, the second problem, the second simulation is on the fluid flow through a pipe. So this is basically the pipe, and if you go back to your static structural, if I zoom in, if you go back to static structural analysis, here what you did, you perform some boundary conditions over this pipe, and you perform the deformation, stress and strain analysis, the static structural analysis. Okay, but here what we the difference in the Fluent is like we want to know how the fluid, that means how the water is going to flow through this pipe, through this hole of this diameter, internal diameter. Okay, so we do not want to perform the simulation this outer diameter, like this pipe made of maybe the plastic or the aluminum, the steel, whatever. We do not want to perform any analysis on this structure. Rather than, instead of this, we want to perform inside this pipe how the fluid is going to flow. So that's why, as I said, in this hollow shape, Ansys cannot perform or generate mesh. We have to generate mesh to perform the simulation, to solve the differential equation. So in this hollow shape, it's not possible for Ansys to perform the simulation to solve the differential equations. So that's why this the pipe has been transformed into this shape. So you see here the inside is solid. So because of this solid geometry here, now Ansys can discretize and also generate the mesh. So that is actually the very basic difference from any actually the structural analysis and the fluid analysis. So you have to make sure that whenever, definitely the fluid is definitely going to flow in a hole of this pipe, or maybe where there is nothing, uh, on that particular thing the fluid flows. So but if you analyze, take this analysis like in this hollow shape and perform the simulation on, this is not be possible, because to do some analysis, when you do some analysis in the statical structure, the mesh has to be generated. So in this hollow shape we cannot generate the mesh, and we cannot perform the solve the differential equations and get the solutions. So that's why these things has been filled with this solid structure, so that here the meshes can be generated and we can have our solution. So that is the fundamental difference between the fluid analysis and the structural analysis. Okay, so this is basically an example of the internal flow. But if you want to, let's say, analyze like how the air is flowing along this uh, car or the jeep. Okay, so what you're gonna do, so this is the car. So if you want to do the analysis, the structural analysis, the what kind of a stress and a strain on the bodies of the structure, then you can do the structural analysis. But we want to know like the how the air is going to flow over this car. So we have to determine a domain, a region. Okay, so in that we put this car, so that in this region we can do the analysis, you know. So you see there is some kind of an enclosure or the domain has been created to perform the simulation of the analysis that how the air is going to flow over this car. So basically when the structural analysis was done, this only car was sufficient. But as we want to know this is an external flow, the air is going to flow like this, you know. So to do the analysis, we have to generate the mesh, and we have to solve the differential equations on that particular meshes or the points or the nodes. Okay, so to do that, an enclosure or a domain has been created, and within this domain there is actually this car has been placed, so that now you can apply the boundary conditions on these two places, and you can perform the analysis that how the air is going to flow. Okay, so that are some basic fundamental differences between the CFD, the fluid dynamics, the computational fluid dynamics, and the structural, the finite element methods. You know, in the structural analysis, basically the finite element methods. Okay, you discretize and you apply the boundary conditions, and you solve the differential equations on to that particular points or nodes, and you get your solutions. But here, as you see that we want to know the internal like flow or maybe the external flow analysis. So to do that, we have to define some domain or region. Okay, so within that region we can apply the conditions, and we can have the differential equation solved. So that is actually the fundamental differences between the structural analysis and the computational fluid dynamics. That means the Fluent or the saved analysis. Okay, now there are some the material properties. Okay, so as you know, like when we perform the structural analysis in the first two activities, where we did actually we need to add some materials in Ansys workbench. We went to the engineering data and add some materials, and there we had to input some properties like the modulus of elasticity, the Poisson ratio, okay, the density, and like that. Okay, but in this case, the material is basically the water or maybe the air or any other fluid. So the basic two like the properties that we'll be using for the material properties is basically the density, you know, because basically the density and the viscosity, you know, these two properties, the density and the viscosity. Okay, if I make it bold. So these two properties are the most essential properties that means to characterize the material. That means either it can be an air, it can be air, or it can be water or something. Okay, so that is regarding the material properties. And regarding the boundary conditions, okay, so there can be the two boundary conditions, like one is in the inlet and one is the outlet. Okay, so if I show you here, so this is our inlet and this is our outlet. Basically what we did in the structure analysis, there were two conditions. One is like the loading conditions, and another one is the constraints. Constraint means it was maybe fixed by some faces, some surfaces are made some surfaces are made fixed so that we can do the analysis. So here those are the constraints. Okay, so here basically and the loading conditions, okay, like that amount of Newton of force has been applied, that amount of pressure force has been applied, and like that. Okay, so this kind of conditions we had in our structural analysis. But in case of the fluid analysis in the inlet and outlet, basically in the inlet we can have either like the velocity of the fluid or the mass flow rate. Okay, and the velocity of the fluid or the mass flow rate of the fluid. Basically this velocity or the mass flow rate is basically working as a constraint. Like whatever the constraint conditions were in the structural analysis, that will be replaced by the velocity and the mass flow rate. This constraint was where like it was fixed with some you know, surfaces. So basically that condition will be replaced here. Instead of fixed, we will be providing some mass flow rate at the inlet, okay, or the velocity, okay. If the mass flow rate is provided, basically the velocity, the velocity you directly can provide, or you can provide in terms of the mass flow rate, okay. So if you provide the mass flow rate, then basically we know the equation for the mass flow rate, that is m dot, basically rho av. So from that equation, basically Ansys can determine the velocity of the inlet, okay. So most likely we in the inlet will be using the mass flow rate or the velocity of the fluid, and the outlet we can have the pressure boundary condition, okay. The pressure boundary condition, like at the outlet what will be the back pressure of the fluid, okay. So that can be the two conditions. One is the inlet conditions and another one is the outlet condition. So you may ask a question like, why cannot we like, is it possible to apply the mass flow rate on the outlet boundary condition? Okay, it might be possible, okay, but you have to know, you have to divide, or not divide, actually you have to make sure that when you actually set your boundary conditions, like in the inlet we have what input, let's say the mass flow rate of 15 kg per second, okay. So if you put the boundary conditions at the outlet, make sure that whenever you put these boundary conditions, the mass flow rate, or the conservation of the mass flow rate, the conservation of the mass needs to be satisfied. That means throughout this whole region the mass flow rate does not change, okay. So if it is 15 kg here should be 15 kg. So if you put here, let's say here 15 kg, you put here 10 kg per second, so there is some kind of the mass conservation is not preserved, okay. So that's an issue, okay. So but if you somehow some sections, like here another nozzle, here another nozzle, so on to that nozzles the mass flow rate will be different, but all along the mass flow rate should be preserved. You have to input your, or make sure you have to put the mass flow rate as an outlet boundary condition in such a manner that the mass flow rate or the mass conservation is preserved. So that needs to be sure, okay. So that is basically the regarding the boundary conditions. And there is another boundary condition that we need to think about, is actually basically the wall boundary condition. Whenever a fluid flows along the wall, what happens? This is, let's say this is a wall, okay. This is a wall, and on the top there is another wall, the boundary wall, okay. So what will happen to the fluid at the whenever this fluid is going to interact with the wall? What will happen to the velocity of the fluid? It will be 0, because of the no slip boundary condition. If you have studied or read the which one, the fluid mechanics, here there is no slip boundary condition. That means whenever the fluid is going to interact with the wall at the boundary, so at that place the velocity becomes 0, and where the velocity becomes high? At the middle, okay. So the velocity profile will look like something like this, okay. So at the end it is 0, at the top it is 0, because of no slip boundary condition. So make sure that by default Ansys sets the wall condition as the no slip boundary condition, but whenever you're dealing with the wall or the surface, make sure that you apply the no slip boundary condition, okay. So that are some basic fundamental discussions on the Ansys Fluent or the CFD analysis. Some differences have been discussed compared to the structure analysis. Now what we're going to do, we're going to perform these two simulations, okay. One is this one. This is a 2D simulation. You see, this is a 2D cross section, the flow characteristics of an incompressible fluid, water, in a 2D cross section. So this is a 2D cross sections. The length is given as 200, sorry, it should be 200 millimeter. It's 200 millimeter, and the hydraulic diameter is given as 10 millimeter, okay. And we have to solve for the laminar flow, and with a Reynolds number of 1000, okay. So if the Reynolds number is given, as I said, in the inlet, what we need to put? We need to put either mass flow rate or the velocity. So if the Reynolds number is given, what is the equation called the Reynolds number? Rho Vd by mu, okay. So rho Vd by mu. So from that equations we have the D, that means hydraulic diameter. That is also given, and we have the rho of the water and also the mu, the viscosity of the water. So if these things are known, you can determine for 1,000 real number what should be your velocity of the fluid. Okay, so that should be in the boundary condition. Okay, now let's actually move to the Ansys workbench. As we know that we'll be actually performing in the Ansys workbench because here all the programs have been set, you know. So we have to use what? Ansys Fluent. Okay. So here you see, previously we dealt with the static structural, but now we have to open the Ansys Fluent. Okay. So if I double click, it's going to open. So for these two simulations where the geometries have not been provided because these are very simple geometry, so we're going to just draw it in the Ansys design modular. So this is basically the Ansys Fluent flow. So we're gonna create the geometry first. So make sure that as it is a 2D simulation, so we make sure that you have changed it from 3D to 2D. Okay. Now go to geometry and edit in design modular. Okay, edit in design modular. So if you open it, it will take some time. I think, do you understand how we're gonna determine the velocity from the Reynolds number? Actually, the Reynolds number equation. Reynolds number equation is rho Vd by mu. So from here, D should be the hydraulic diameter, and rho and mu is known for the water, and Reynolds number is 1,000. So from that, we can determine the velocity. So this is the design modular. I think you're familiar with this one. You have used in your first two activities for the static structural analysis. So similarly, we're gonna just use that. So make sure, first of all, we're gonna change the unit to millimeter, and we're gonna go to the Z, XY plane. So what you're asked to draw here, this rectangle cross section, okay, this 2D rectangle cross section. So we're just gonna use, and which is the length should be 200 and the diameter should be 10 millimeter. So if I just use go to the sketching and go to draw a rectangle here. Okay, so that's basically it, and you have to give the dimensions, and the dimension should be, this one should be 200. Okay, 200, and this should be 10 millimeter. Okay, this should be 10 millimeter. Okay, now what we need to do, we need to, as you know, this is a 2D simulation, so we have to go to the concept and surface from sketches, and we have to select the geometry or sketch and apply. Let's say the thickness we use, let's say 5 millimeter. Okay, and you have to generate. So our geometry has been generated. Okay, okay, now we get out from here, and to generate the mesh, we're going to open the Ansys mechanical. Okay, so if you go to the mesh and double click, it is going to open the Ansys mechanical, and here you have to define the mesh actually, and also you have to define the inlet, outlet, and wall. Okay, so it's going to take some time. Okay, so Ansys mechanical has been opened. Now what you need to do, first of all, as I said, we need to define the inlet, outlet, and surface. Okay, so that is our inlet, this section, and this is our outlet, and this is the whole surface. Okay, so we're gonna name it, so we have to make some sections. So to do that, you go to the model, you right click and insert name section. So you have to name the sections. Okay, so first of all, select this section, that should be your inlet. Okay, so change, rename it and make it inlet. Okay, so again, go here, insert name sections, select this one, and we're going to name it, apply, we're going to name it outlet. Okay, rename, we're going to make it outlet. Okay, and again, if you go here, insert a name section, so you have to select this whole the surface. Okay, so that is selected and apply, and we're gonna call it, you can say surface or wall, whatever. Okay, that's gonna call it surface. Okay, now we're not gonna make a lot of changes in the mesh. Okay, we're gonna just change the mesh. As you know, when you perform the static structure analysis, the element and the number of elements and number of rows, it does not need that you need a very higher number of mesh. Okay, if you needed say 5 millimeter of meshes, it was somehow good, but for the CFD analysis, we need a very finer mesh. Okay, so for that the element size should be less. Okay, so for this analyze, we're gonna use the element size, let's say 0.5 millimeter. Okay, and we're gonna do some inflation layer. Okay, we're gonna because what we need, okay, here in this experiment or in this activity, we need to analyze the formation of the boundary layer. Okay, formation of the boundary layer, or how the velocity curve is formed along as the fluid flows along this cross section. Okay, so this is the two wall, this is one wall, and this is the top wall, and this is the bottom wall. Okay, so these two walls, what will happen, these two walls, at these two walls, at the very edge of these two walls, there should be no slip boundary conditions. Due to that, the velocity should be 0. Okay, so but to analyze the formation of the boundary layer and the velocity curve, we need to have a very finer mesh along this boundary layer. Okay, these sections and these sections. So to have this finer mesh, we're going to use this meshing is actually very it's mostly used for the CFD analysis. We're going to use this inflation. Okay, so we're going to select this whole surface and apply, and you see here the boundary needs to be selected. So we're going to use the two boundaries. Okay, one is this one and another one is this one. Okay, and then apply. Okay, so these the two edges have been selected. Now we have to use this smooth transition to the first layer thickness. Okay, 1 minute. First layer thickness, and then the maximum layer that we want that the mesh should create. Okay, that we're gonna stick to, let's say 20. So the maximum amount of layers in this along the boundaries, that should be 20. So 20 layers will be created, and on that layers they will have a very finer mesh. Okay, and here you see we have to first layer height. What should be the height of this first layer of 20 layers? Okay, so it should be, let's say 1 e to the power minus 3, sorry, minus 2. Okay, 1 e to the power minus 2 millimeter. Okay, now if you now generate the mesh, you'll see how it looks like. Okay, it's going to take some time. So mesh are generated. You see what I was talking about. You see along this boundary layers, there is a very finer mesh, and the layers have been created. these layers, you know, that the how many layers are there? 20, and the thickness of each layer is 1 to the power minus 2. Okay, so that is basically the inflation mechanism, because we need like the finer mesh there to have a better analysis of how the formation of the boundary layer. Okay, so now our work with the Ansys mechanical has been done, so I can close it. Oh, why is it taking so much time? Don't just crash. Okay, I think it's done. I know. Let's hope that it's done and update it. So there's a bold sign, so we have to update it. If it is correctly done, I think there will be a tick mark. Okay, so it's done. Now you see there's a tick mark. So now we're gonna go to the setup. So that will basically open the Ansys Fluent. So we're not gonna change anything. Whatever the settings is there, we're gonna use that. Okay, so our geometry has been opened. So now what we need to do. So first of all, we have to, as we are doing the analysis on actually a laminar flow. Okay, so for that, go to the models. Okay, go to the models and go to the viscous SSTK omega. So go here. So there, these are basically analysis for the turbulent model. Okay, if you deal with the turbulent flow, then based on your like the flow, fluid and analysis, you have to actually use any of this. But as we are sticking to the laminar analysis, so we'll be just using the laminar. Okay, that's it. So now go to the material. So we have to select the material. See, in the fluid, the material has been selected as air, but we need water. So to have water, go new and Ansys Fluent database. So from here, you're going to find the water liquid. Okay, so this is what sorry, this is water liquid. Okay, so if you check that and copy, close. Okay, so water has been added. Okay, to a liquid. So now go to the cell zone conditions. Go here and go to the fluid. Okay, the fluid will be using it is basically in default is set at air, set as air. We're going to change it to water. Okay, so make it okay. So if you check here also on the surface, and this is also the water selected. Now we have to apply the boundary conditions. So there are inlet, outlet, and the wall. So in the inlet, we're gonna apply what? We're gonna apply as the Reynolds number is given. You have from that Reynolds number, you have to determine the velocity. Okay. So for that, if you go here, so this is your inlet, and if you do the calculation for 1,000. So Ansys is crashed, unfortunately. So I have to open it again. So this is actually a problem dealing with the crack softwares, and the performance is very unstable. Okay. So is it imported? So basically what I did, I'll be doing again. So let's make sure that here the steady is selected because we're doing the steady analysis. So go to the model and go to the viscous SST omega, and from here select the laminar, okay, and select OK. So now we have to actually determine the materials. So the material should be water. So if you check the fluid, only air is there, so we have to create a new material. Okay, new material should be added. So if you go here and go to the Fluent database, from the Fluent database you're gonna have the water liquid. Okay, if you uh, copy, so it's gonna be here, water liquid. Okay, and then close. So this water liquid is here. Now for the cells and conditions, for the cells and conditions for the surface, we have to select the fluid as water. Okay, so you know the material is selected air, we have to change it to water. Okay, now the boundary conditions. Okay, so the inlet, outlet, and the wall. So in the inlet, as I said, the Reynolds number is given. From that you have to calculate the velocity. So if you calculate the velocity will be 0. It should be 0.10018. Okay, and you make it a magnitude normal to boundary and make it absolute. Okay, and okay, so the inlet boundary condition has been applied. And if you go to the internal surface, you'll see, as I said, in the internal surface, what should be the boundary condition? No slip boundary condition. Okay, no slip boundary condition. So it is basically by default, Ansys actually sets that. And if I go to the wall, sorry, the outlet, sorry, at the outlet we have to give what in the outlet, what we are given. There's no, the pressure should be 0. Okay, and the gauge pressure should be 0 at the outlet. So if I go to the Ansys point, and the pressure should be 0. Okay, so you apply it. And as I said in the wall, sorry, that was not in the internal. At the wall, the boundary condition should be no slip boundary condition. So if I expand it, if you go here, surface body, if you see here, the no slip boundary condition has been applied by default. So you do not need to change anything of that. So now to start the analysis, you have to go to this initialization. Okay, and we're going to use the hybrid initialization. So to start the fluid analysis, the safety analysis, you have to start from a stable form of the fluid flow. Okay, so to do this, to do the initialization, we have to actually use either hybrid or standard. So for this simulation, we're sticking to the hybrid initialization. And if you initialize, you're going to initialize the solution from a stable flow rate or stable velocity. Okay, so the initialization has been done. So now we have to go to the run calculation. Okay, so if I go to the run calculations, here you see the number of iterations. So how many iterations do you want to get the solution, for the nodes? Okay, so similarly you can use the higher the iterations, the higher the computational power, but the more accurate the solution is. But basically this kind of normal actually analysis, I think 150 iterations is good. So I am sticking to let's say 100. Okay, so there should be 100 analysis. And if you do the calculations, you see these are the residual. Okay, and as the residual value is approaching -4, -3, and so on. Okay, so the black one is the continuity residual, and the red one is the x velocity, and the green one is the y velocity. So you see the residual is reducing as the number of iteration increases, and after sometimes it does not decrease anymore. So we can actually approximate that the solution is somehow converged. Okay, so it's done. Now if I want to plot, okay, so for that let's say first of all we're going to make the contour plot. Okay, so for the contour plot, let's say we want to see the pressure, the static pressure, you know, the whole interior surface. Okay, so if you save display, so this is actually the pressure. How does the pressure look like? Okay, and if I select the surface body, let's say what it shows is actually these two bodies. Okay, at these two ends, how the pressure is there. Okay, so basically if you want to see the along the whole body, it should be the interior surface. This is how the pressure look like. So if I want to see, let's say, the velocity, okay, and the velocity magnitude and the whole body selected, how it looks like. So it looks like something like this. Okay, what we can see the wall shear stress. See the wall shear stress. Let's see the pressure again, because static pressure display. See what happens whenever you do any analysis. You have to know that at the inlet, sorry, at the inlet the pressure should be higher, okay, and the outlet the pressure should be lower. So at the inlet there's red marks, red zones, so the pressure is higher. But if you go to the outlet, it is almost blue, and the blue is the lowest pressure. So pressure, the fluid always flows from high pressure to lower pressure, so that actually verifies that. Okay, now if I want to see the velocity curve, sorry, not the velocity, the profile of the velocity, okay, at a certain distance, the whole length is 200 meters. So let's say at certain points we want to see that how the velocity curve looks like. So for that you have to go to the surface, okay, and new, you have to create a new line. Okay, so this is x direction, this is y direction. Along the x direction we're gonna go, the whole length is 0. What 2, and it's in meter, you see, 0.2. So I have let's check at 0.1. okay, let's check at 0.1. so I am gonna name it line 0.1. So let's say name it A. Okay, so and y, what should be the total? We want along the total hydraulic diameter. The hydraulic diameter is 10 millimeters, so 0.01. Okay, so now if I let's create another line. We want to see at, let's say the total length is 0.2, so let's say we want to see at 0.18. okay, this is the B point, let's say. Okay, create, close. So to plot, let's go to the plot and XY plot, new, right click. So here we're going to plot the velocity. Okay, and we're going to plot what velocity? We're going to plot the x velocity, because in the x direction the velocity is going to change. Okay, so if you plot it and we want x, we should invert it. Okay, because it will be something like this, the profile should be something like this, but we're going to see it like this. So that's why it was 1 0. We're going to making it, inverting it, 1 0. Okay, and we're going to select the point, let's say A. So how will it look like? See, it looks like this. So you see from if I see here, so from this is the diameter and this is how the velocity is changing. Okay, so let's say if it can be seen is with the y velocity. No, it is basically the x velocity. Okay, basically that is creating the profile, you know, the profile, something like this. Okay, I think you have seen this in your fluid mechanics class. Okay, now let's check in the B point. Okay, this is something like that. Okay, let's check in the B point. So see, it is getting a stable curve. So that means the boundary layer formation has been completed. No, it is becoming this is basically the formation of boundary layer. You know, basically it takes 10D length. Basically, theoretically, that means if the length is hydraulic diameter is 0.2, 1, and then 10 means 10 into 0.1. Okay, so that is the length. Basically it 0.01. So at 0.1 at 100 millimeter, it's supposed to form get the velocity profile. Okay, the actual velocity profile. Okay, so that is how you need to actually see the velocity profile at different points. We have taken 2 points at C. At the point A, it was not totally formed, but at point B, it was almost forming the curve, the velocity profile curve. Okay, so that's it. That's how can I check. So that is regarding our first simulation. Okay, so that is regarding our first simulation. Okay, we're gonna save it. We go to the Ansys workbench, and let's just save this to the documents. Okay, let's say the activity 301. Okay, now let's perform the simulation on the second one. Okay, so that will be your 2D simulation, and that is also we're going to perform in the Ansys Fluent. Okay, so let's close it. Go to the Ansys workbench. Now if I again check the B1, so we have to show another simulation. So here make sure that it's in 3D. So we have to create the geometry. So the geometry configuration is given. So the diameter should be 10, and that is should be a cylinder, and the length is given as 1 meter. Okay, the length is 1 meter, and the diameter is given as 20 centimeter. So to draw that in the Ansys, we have to go to where? The design modeler. Okay, to go to the design modeler. So there is a 3D geometry. So, and as it is a cylinder, so we're going to just extrude it. Okay, with a 20 centimeter diameter up to 1 meter length. Extrude. So select Z and XY plane. Make sure that units in meter, because here the extrude length is given 1 meter. So what you need to do, you have to draw a circle of 20 centimeter diameter. Okay, so draw the circle here. Okay, the diameter should be 20 centimeters, so that should be 0.2. so it is very small. So if I zoom it, so that's what it looks like. Now what we need to do, we need to extrude it. So if I select extrude, select this sketch, and the extrude apply, the extrude should be 1 meter. So it is by default 1 meter. If it is any other value, you have to change it, because but in our activity sheet it is given as the cylinder length is 1 meter. So we're going to extrude it to 1 meter. Okay, design modeler, and if you generate it, so it has generated. You see this length, this is diameter 20 centimeter, and this length is 1 meter. So this has been generated. So it's done. Okay, now you can close the window. Okay, now if I go to the Ansys workbench, and we have to go to the mesh, so that will open the Ansys mechanical. So here, what is the inlet condition? Inlet, we have given the mass flow rate of 15 kg per second, and outlet, the back pressure is given as 100 kilopascal. Okay. Here we're not going to change anything with the mesh, okay, because we're going to keep it as it is. Okay, unit is millimeter. So make sure that we have to we need to do, we need to define the sections, because as you see, when you opened it in the Ansys Fluent, there was inlet, wall, and outlet. So you have to define it from here. Otherwise, in the Ansys or Fluent, it cannot determine that. Okay. So from here, similarly from the first simulation, you have to insert the section. Okay. Select this one, this surface, apply, and you have to rename it to inlet. Okay. Now again, insert, we have to use the name section, and this is our outlet section. So we're going to name it to outlet. Okay. Now again, we have to insert name sections, this whole wall. Okay. That should be called our wall. It's done. So in the mesh, I'm not doing anything, just this 51 millimeter length was there. So for this analysis, I'm going to use in the activity is given. So if I go here, yes, the mesh size is given as 15 millimeters. So for this analysis, I'm going to use the mesh size, the element size is 15 millimeter. Okay, if I now generate the mesh, so the mesh has been generated. Done. You can close the tab. See, there's a bold sign. Again, you need to update it. And similarly here in this active simulation as well, at the wall we'll have a no slip boundary condition, and by default Ansys will have it determined. Okay. So now it's tick mark. Now if I open the setup, whatever it is, I'm not changing. Okay, so give it some time. So it's opened. So this is your geometry. So similarly, what we done in the first simulation, we'll be doing here. Okay, but the conditions are changed. So first of all, what you need to do, we go to the model. We have to make it for the laminar analysis. We're not considering any turbulent flow analysis. So go to the viscous SST omega, and here select the laminar flow. Okay, done. Now what you need to do here, the material. Here the material is given, the properties are given. Okay, so if I go here, the rho is given and the viscosity is given. Okay, so let's show you how to input that. So if you go here and the fluid, you go to the new. Okay, so in the new, you see here we have to put let's say the name it water. Previously we had taken it from the Fluent database. You can also take it from there, but let's say if you want to change it, as I said from the very first of my lecture, here the material properties should be either density and the viscosity. This is the most two crucial properties that we'll be using to define a material. Okay, so here the density should be given as it should be 999, and what is the viscosity given? If I go back here, it is 8.9 10 to the power minus 4. So it is 8.9 e to the power minus 4. Okay, so it's been created. So you see this water, it has been created 8.9 10 to the power minus 4. Okay, so it's done. So now what we need to do, we need to go to the cells and conditions. So we have to make sure this has taken as fluid, as water. Okay, so this has taken as air, we have to change it to water and click OK. Similarly as the first experiment, and in the boundary condition we have to, you see there is inlet, outlet and wall. this has been recognized by the Ansys Fluent, and that we had created in the Ansys Mechanical. Okay, so here we have to use the inlet and the inlet. So by default, it is asking me to give the velocity, and as I had discussed at the very first of my lecture, but we are given the mass flow rate. Okay, so if I go back to our manual, so mass flow rate is given, okay, 15 kg per second. So we have to change the type. If you right click type, it should be mass flow inlet. Okay, so now you can give the mass flow rate. Okay, so see the mass flow rate you can determine. So the mass flow rate is 15. Okay, and you have to change it. The reduction vector is to normal to boundary. Okay, and the mass flow rate should be 15, and you have to click OK. So internal, you don't need to do anything. In the outlet, we have a back pressure as 100 kilopascal. So if I go here, okay, it is 100 kilopascal. So it should be 100 e to the power 3. Okay, so if you apply, so if you check here, it's 100 actually 100 kilopascal. Okay, it's in the unit is pascal, so that is showing in pascal. Okay, done. And similarly, if you check in the wall, it should be no slip boundary condition by default. That we do not need to change anything about. Okay, now similarly, if I go to the initialization, as I said, we have to start initialization, start to iterate the solutions from a stable point. So to do that, we're going to initialize, and also for this we're using the hybrid initialization. So if you initialize, you can initialize your solution. Okay, the initialization has been done. So now you have to go to the calculations, and you have to give sorry, not here, you have to go to the run calculations. Okay, so here you have to give the number of iterations, and I have discussed what is it. You have to how many times you need to iterate to get the solutions. So for here I am using, let's say 50. Okay, 50 iterations, and let's say calculate. See, this is the continuity equations. The residual has been calculated. So it's at the level of e to the power minus 4, e to the power minus 5. So it's good, you know, and at some point it's not somehow changing. So when the residual does not change, that means your solution has converged. Okay, so yeah, our calculation has been completed. So now we have to plot. Okay, so we're going to plot the contour plot. So similarly, go to the contour. Let's plot the pressure. Okay, at the 3 we want to see the pressure at the inlet, outlet, and wall as well. Okay, 3. Now if I show it, so it looks like this. Okay, so remember, you always have to interpret the result, you know, interpret the result. Okay, see, at the inlet is a high pressure, at the outlet there's a low pressure. So always fluid flows from high pressure to low pressure. So it has been satisfied. If I want to see the velocity, okay, let's say, so this is how the velocity looks like. Okay, so mostly you see at the wall it is blue. Blue means what? Blue means 0, no slip boundary conditions. And if I see here, the hair and the inlet, it is red, so almost the highest velocity. So here is also we're interpreting the result well. And if I want to see the wall shear stress, you have to go to wall fluxes, and if you select the wall shear stress, and I just want to see the wall shear stress at the wall. So I'm not selecting inlet and outlet, just wall. And if I show display, see, so this is how it looks like, you know, this is the distribution of the wall shear stress. So that is how you can do the analysis in the Ansys Fluent. So these two analyses are very basic. So the basic, the main objective of these two simulations is to make you familiar with the Ansys Fluent. We're not solving a very complicated geometry, or not solving a very complicated problem. Okay, to make you familiar with the very basics of the Ansys Fluent, so that when you perform and when you need to perform the analysis for your thesis, project, or anything, you can have a very basic idea, familiarity with this software. So that is basically the objective of this lab and for this activity as well. So thank you all for joining. Assalamu alaikum.